This video is going to cover section 4.7 in our calculus textbook. It's entitled Optimization Problems. Optimization problems are commonly referred to as max-min problems as well. These are problems you would have solved in pre-calculus, except you would have used your calculator. Now we're going to use calculus. So an optimization problem seeks to find the largest or smallest value of a quantity given certain limits or constraints. So there are some parameters we need to follow, and that's going to be the crux of the problem. So an optimization problem is usually expressed in some form as find the maximum or minimum value of some quantity under a given set of circumstances. This quantity that we want to maximize or minimize, we need to express as a function. And under a given circumstances, this will tell us what we need to make that function in terms of. So we can do a quick example, and hopefully that will illustrate what we're doing here. This is an example you would have seen before. A manufacturer wants to design an open box, so no top, having a square base and a surface area of 108 square inches. What dimensions will produce a box with the maximum volume? So we want to maximize the volume. We want to determine what dimensions will do that with the condition that the surface area must be 108 square inches. So that's all of our information. It helps to have a diagram. So you can draw a picture. I'm going to label the sides. The base is a square, so I'm going to use x for the lengths of the two bases. And it's a box, so we also have a height. What we want to maximize, again, is volume. So the volume of the box is going to be the area of the base, x times x, or x squared, times the height, which is h. Now I want to use the first or second derivative test to find the maximum value of the volume. But the equation I currently has x and h, both variables. So if I were to differentiate with respect to x, for example, I would have to use implicit differentiation on both v and h, and that could get kind of complicated. So here's where the constraint or the circumstance of the surface area being 108 comes in. We're going to use that to make the derivative something easier to find. So the surface area of this box, use A for surface area, is the area of the base, which is x squared, plus the four sides, all of which are x by h. So 4 times xh is the area of each of the, or all four sides together. So that's the total surface area. And we know that the area is in fact 108. So if I substitute 108 for A, I get x squared plus 4xh. So my goal now is going to be to eliminate one of the variables. I'm going to choose to eliminate h, which means I'm going to solve this for h.
Please, this announcement is for seniors. Any seniors with a last name beginning with D should see Mrs. Juttle in the office today for cap and gown measurement and diploma ordering. Also, any other seniors who have not already been to the office are welcome to do that at any time in your day that you are available, either on your way in, during a study hall, or before you leave for the day.
So I hope all you seniors enjoyed that message. Sorry about that. But I'm going to continue. We're going to solve for h. And when I solve for h, we're going to subtract the x squared from both sides and divide by 4x. So we're going to end up with 108 minus x squared divided by 4x. And I'm going to take this and use it to substitute for h in this equation. That will give me, way down here, that the volume is x squared times h, which is now 108 minus x squared over 4x. Probably a good idea to do some simplification before we try to take the derivative. I can cancel that x with one of the two and that x squared, and then distribute this x to each of the terms here, thus creating a polynomial. So the volume will be 108x minus x cubed all over 4. And this is our volume equation. This is what we're going to use to find the maximum. So I'm going to go to another page. And we will continue this problem. So the volume we just said was 108x minus x cubed all over 4. So now what I need to do is take the derivative and find out what value of x maximizes v. So if I take the derivative with respect to x, dv over dx would be, that's a constant. So I've got a polynomial divided by a constant. So we're going to simply have the derivative be divided by that same constant. And so it breaks down to simply taking the derivative of the numerator, which is 108 minus 3x squared. Once I have the derivative, I need to find critical points. And I do that by setting dv over dx equal to 0. I also have to consider where the derivative doesn't exist, but the polynomial in the numerator exists everywhere, and the denominator is a constant, so that has no effect on it. So I don't have to worry about that. But if I set 108 minus 3x squared equal to 0, I can then multiply both sides by 4. I forgot that this was over 4. That was the point of multiplying by 4. And these 4s will cancel. And we end up with 108 minus 3x squared equals 0. Our goal is to solve for x. We can subtract the 108 from both sides and divide by -3. That will leave us with x squared equals 36, and then x will be plus or minus 6. Now, I'm going to reject -6 as a possible answer because it can't be the dimension of our box, but it's important because next I need to figure out at those critical points, 6 and -6, whether I have maximums or minimums. So this is going to require us to do a sign analysis. So when I do my sign analysis, I'm going back to the original derivative. Remember, dv over dx was 108 minus 3x squared all over 4. And my critical points are -6 and +6. But if I look at the derivative, it is simply a parabola. And the leading coefficient is less than 0. It's negative, which means it opens down, which we now can say is concave down. So the parabola is going to have this sort of shape. That sort of shape is simply going to tell me that to the left of -6, the function is negative, or the derivative is negative. Between 6 and -6 and 6, the function is positive, and then from 6 on, it is negative. So at 6, we have a sign change from positive to negative, which indicates that there is a maximum at 6. So we have a maximum at 6 of, well, whatever v of 6 would happen to be. We're not asked to find the volume, just the dimensions. And I should, for AP purposes, write y, because the sign analysis is not a sufficient reason. So I have a max at 6 of v of 6, since v prime changes from positive to negative. And that's sufficient. You could write it in terms of inequalities, and that would be okay. Now, that was using the first derivative test. You could also check for the max or the min by using the second derivative test. So if I go to another page and I have my problem rewritten here, the first derivative, dv over dx, was 108 minus 3x squared over 4. If I check the second derivative, which is the second derivative of v with respect to x, then the derivative of that, again, the denominator is a constant, so it stays. The numerator is a parabola, it's a quadratic. That derivative would be -6x.
Mr. McCluskey, please pause to 0.
And the
1.
derivative, v prime, which I'm going to write now, the second derivative at 6 would be negative 6 times 6 over 4, or negative 9. This would also make a maximum at 6, since the second derivative is negative. So I would write again, there is a maximum at x equals 6, since f double prime, or I'm sorry, I'm using f, it should be v double prime of 6 is less than 0. That is the second derivative test. Either one gives us the fact that we have a maximum at 6. Now, the original questions were what dimensions will produce a box. So I not only need to know that x is 6, the width of the base, but I also need to know the height. Recall that the height was equal to 108 minus x squared over 4x. So I need to plug in x equals 6. So the height would be 108 minus x squared, which is 36, over 4 times 6, which is 24. 108 minus 36 is 72, divided by 24 would be 3. So the dimensions that produce a maximum are 3 by 3. No, it's not 3 by 3. It's 6 by 6. 6 by 6 by 3. And that gives us our maximum volume. So that's done in two ways. You can use the first derivative test or the second derivative test to verify that you've got a maximum. Either way works, whichever you're most comfortable with. So, in general, optimization problems. You need to determine what needs to be optimized. You need to write a function for what needs to be optimized in terms of some other parameter. So we did that in terms of the base width. Find the extrema of the function using calculus. So this would be using the first or second derivative test. And then determine which extrema answers the question. If you get a multiple critical points, you got to decide which one is the one that is the answer to the particular question. All right, so we're going to have some more examples to work on in class, and we will see you soon. Thank you very much.